Welcome to the last week of this lecture series. So we have a lecture today and also on Wednesday. So today I will tell you about the classification of these easy quantum groups, and next time about some applications. So originally I planned to save the whole week for the applications. Now my schedule is a bit shifted, so next time when speaking about the applications I will be a bit brief, but I hope you don't mind. So next time this will be more like a survey character, and now I will tell you a little bit how rich this world of easy quantum groups is. Maybe we put this. Okay, so last time I gave a definition of the easy quantum groups, and I tried to motivate at least a little bit why they could be interesting. So once you accept that an object is interesting or a class of objects, you might be interested to know how many of there are there. So what are the examples, right? So this is what we will do today. So yeah, maybe just a brief reminder. So we had a category of partitions. So this is closed under this tensor product, which meant I take a partition, I take another one, put them side by side. Then there was this composition. So this means I have one partition, I take another one which I put below it, and then I just follow all the lines and connect all the points that there are. And I have involution. This means I take the partition and just turn it upside down. And then we also have that two initial partitions are always in our category. Okay, so these are the rules. And of course now we can just play the game, pick some partitions and see what we can generate out of it. And then we can see how many examples there are. And last time I also said that it is also closed under rotation. So this was when I have a partition with k upper points and l lower points, I can take one point and move it to the lower line, or the converse, and also on the other side. And I don't change the block structure when doing this. And often this will be quite nice.
One of the extreme points, right?
Yes, one of the extreme points, only the extreme points, yeah. And often this will be quite nice, because when we want to know if a partition is in the category, we can rotate all of its upper points to the lower line, and then I only have a partition with only lower points and no upper points.
What can be also taken apart?
Yes.
Extreme right or extreme left, what points?
Yes.
That also can be done.
Yes. Yes. Yeah. So if I have a partition, I can take an extreme point from here to below. I can take a lower point to above, and also on the right-hand side. And
That's because it's closed under involution, isn't it?
no, for this we use this when you have a partition. We use this pair partition. And since you have this pair partition, if you do this composition, then you see that here you have k minus 1 points, and here below you have l plus 1. And this point is now here. Yes, and often this is quite nice, because for many things we can then restrict to partitions which only have lower points. Because if we can say something about these, which have no upper points but only lower points, then later we can shift the points to the upper line, and then we have the results also for the others, and vice versa. But I will say about this a little bit in more detail in a second. And then we already had the lemma that if you just start with these two initial partitions and you check what comes out if you use these operations, and you create all the partitions that come out, that's exactly the non-crossing pair partitions. So it's only those partitions where the lines connecting the points do not cross, and it always connects one point with another, only 2 points. And we also had, if you take this partition and this crossing partition, so this is one upper point is connected to the right lower point, and the other one with the right upper point. So if you take this partition plus these two, then you will get all pair partitions. And you do not care whether the lines cross or not. And then we also had this category, which means I take the partition which consists just of one lower point. So this is defined as this partition which only consists of one lower point. So if I take this partition and also this one connecting 4 lower points, then I get all non-crossing partitions. And if I add the crossing partition, then I get all partitions. So this was something we discussed last time towards the end. And yeah, so natural new examples are this is one new category, and also this, if you just take the 4 block, for instance, these are 2 new categories. Okay, so you can convince yourself that this is the category where all blocks have size either 1 or 2, and this forms a category, and this is then a category of partitions. And if you associate a quantum group to it, this is the quantum group called Bn+, which is given by the C-star algebra generated by all Uij, which are self-adjoint, such that the matrix U is orthogonal, and the relation which look like this. So if you sum the row or if you sum a column, then this will always add up to 1. So this is almost like with Sn+, right? With Sn+, you also have that these Uij are projections. I don't need that they are projections here. Here it's just I have the Uij's and they sum up to 1. If I want to have that they are projections, then I have to add the 4 block partition, and the relations corresponding to this one will give me that the Uij's are projections. Okay, so this is one new quantum group, or also we have Hn+. And this is governed by these relations. Oops. And if you check, then this is exactly the relation that comes out when you compute this partition, or rather this one, where you connect 2 upper points with 2 lower points. Of course, the categories of these two, they are the same. Because if I have this partition in my category, I can rotate the 2 upper points to below, and then I have this partition. So I have this partition inside, which means this category is inside this category. And conversely, if I take this partition and I move 2 points to above, then I get this partition, so they are the same. Okay? And the relation, if you just check what it means, that this is in the intertwiner space, the GP associated to this. Last time I wrote down explicitly how to come from a partition to relations. If you check it, then it's exactly these relations here. And in fact, if you add the crossing partition, last time I told you that this means that the Uij's commute. And in this, so this corresponds then to a group, and the group is called Hn, and that's this Reth product that we had in our very first lecture. In the very first lecture, we were computing the quantum automorphism group of a certain graph, I have 2 points, connect them, 2 points, connect them, 2 points, connect them. So this was a graph. Or we also took the cube and asked for the automorphism group of that. And this was the automorphism group. And if you write down the relations of this group, then you pass to the functions over this group, then you will see it's exactly this C-star algebra where the Uij's commute. In this sense, this Hn plus is the free quantum version of this. Okay. So you see that this is a quite systematically way to go from groups to quantum groups, right? If you see that a group has this intertwiner space, then you just forget about this partition and just use the non-crossing ones, and then you get a free quantum version of this. Okay, so that if we could now ask, okay, what are all examples of easy quantum groups, and we could first restrict to those categories which are contained in NC.
This group is a finite group, like a Z2 ring product with S and Z.
Yes.
The first two examples, are they infinite dimensional C-star algebras?
Are they what? Sorry?
Are they infinite dimensional C-star algebras?
Yes. These are infinite dimensional C-star algebras.
I think there's some restriction on n, right? At least for Pn.
Oh yeah. There's a restriction on n. Yeah. So if n is large enough, they are infinite dimensional. Yes. Yes. Okay. So we could now restrict ourselves to categories of partitions which are not contained in all partitions, but only those in the non-crossing ones. So maybe let's start with this. Maybe that's an easy beginning for our classification, and there are exactly 7. There are exactly 7 free easy quantum groups. This means 7 categories C which are contained in NC. So only non-crossing partitions involved. And we know already some examples, namely we know
How do you distinguish two categories? I mean, 7 means
how to...
sets, is it? Okay, sorry.
Yeah, I mean, I distinguish them as sets. But if I really want to prove that two categories are the same, usually that's easy, because you just say that all partitions that are in one, you have to say that they are generated in the other, and vice versa. But if you want to say that two categories are not the same, this is a bit more difficult usually. You can try to use some combinatorial means for this, or you pass to the C-star algebras. For instance,
Write down 7 and quantum groups that they turn out, each one of them are non-isomorphic as quantum groups.
yes, if you consider the isomorphism that maps Uij to Uij, there might be other isomorphisms. I don't say something about this. I only say that if I have one quantum group generated by Uij, another one mapping Uij to Uij, there are 7 different ones. Yeah.
There are no soft methods to say that they are different as quantum groups, like fusion rules are different. That doesn't depend on Uij mapping.
That's true. I mean, this is you could compute the fusion rules and see if they are different. Sure, but I'm just saying that you need some more machinery if you want to distinguish it. I mean, you can do it by combinatorial means, and in some cases, but sometimes you need more machinery. And for instance, this Bn plus can be proven to be isomorphic to Un to On minus 1 plus if you do not take this Uij map to Uij, but a different isomorphism. Okay.
Quantum groups as just as C-star algebras.
As quantum groups, yes. Yeah. So but here, when I say there are exactly 7, what I precisely mean here is there are 7 categories of partitions. Yes. And when I associate the quantum groups, and then I have certain maps mapping Uij to Uij, and those are not isomorphisms. Okay, so what are these 7? We know already. Okay, this one is one category which only involves non-crossing partitions. So this was one of the examples here. So you can convince yourself that all these categories, all the partitions that come out here, that there's no crossing involved. We had already this one. We had already the 4, and maybe I'll write it like this. The 4 block and the singleton, and the 4 block 1. So these are already 4 examples, and there are 3 more, namely this one, this one, and this one. They are contained in each other. Okay, so this is the result. There are 7 quantum groups and 7 free easy quantum groups, and they look like this. And I just want to give you a slight flavor of the proof, just to see how we play around with the combinatorial structure here. But I don't want to give the full proof. So for instance, I could start saying, okay, so let C be a category of partitions. So I just take one, and now I do a case study. Namely, I assume, for instance, that these 2 partitions are in my category. Then, of course, also the smallest category generated by these 2 guys is in C. Okay, this is the definition of this, writing it like this. It's the smallest category containing these 2 things. But we saw already that this equals NC. On the other hand, this C is contained in NC. Okay, so there's only one category of non-crossing partitions containing these 2 elements. Okay, this would be one case. In the second case, I could be, for instance, I could say, now I want to have the singleton inside, but not the 4 block. Another case. What happens then? Then, of course, this one is in C. And on the other hand, if P is a partition in C, then all blocks have lengths 1 or 2. Okay, how comes? Okay, suppose P has a block of size at least 3. How does P then look like? Well, up to rotation, P is of this form. And here are some points, some points, some points. Okay, so P has a block of size 3 or more than 3. So I can rotate all upper points to the lower line. And this partition will again be in C. So there's definitely one partition having no upper points, only lower points, a block of size 3. Now, the first point might not belong to my block, but I can then rotate these first points to above and then to below. Okay, so I can rotate all the points that are before my first point of the block to the right-hand side. So I can assume that P is of this form. And now, composing,
To me, there are points between the compared with alternative. That's why you put dot dot.
yes, exactly. Here are many points.
Three consecutive points, right? Correct?
No, it's not 3 consecutive points. Yeah, so there are many points which have any structure. Yeah. And they might, of course, they might even be connected and so on. But I compose this partition with this one.
So they cannot be.
Oh, no, it's a non-crossing partition. They cannot be connected. That's true. Yeah. I mean, I'm referring to a result which is a bit more general, but here it's non-crossing, so they cannot be connected, yes. But I compose this partition with this partition. Okay, so here the identity partition. And here only these singletons which I turn upside down. I mean, since the singleton is in my category, by involution, the one which is turned upside down is also in there, and this is just the tensor product of these partitions. So if I compose it with this, what do I get? So this yields that this 3-block partition is in my category. I erased all the other points. And of course then, the 4-block, which is just the 3-block, tensor product the 3-block, which is in my category, composed with this partition, is in my category. And this is a contradiction, because I assumed that the 4-block is not in my category. Okay, so I see that if I take a partition from my category, all blocks have size 1 or 2, and I can check that those partitions may be generated inside of this category. Okay, so if I take a partition which has only blocks of size 1 or 2 and which is non-crossing, then I only need these 3 partitions and the category operations in order to generate it. So thus, this category must be of this form. Okay, so now we have done we have done this one, and we also know this one, and yeah, okay. So then you just continue with your cases, right? Then now you assume that the singleton is not in there, and the 4-block is, or the 4-block isn't, and so on. So if you do this case by case, then you will see that in the end you will end up with this list. Okay, but this is somehow the flavor, and you can do it by direct combinatorial considerations. Okay.
Can you prove they are not equal by considering choose 2 cases?
So by showing that by proving that they're non-equal, for instance, I describe that this category is the one consisting of all blocks having size 1 or 2.
Okay.
This category of
all the inclusions are proper also.
yes, they're all proper, and for each of these things I have an explicit description, and this tells me that they are not the same. They cannot be the same. Yeah. Another way of doing it is, as I said, yeah.
By explicit description, you mean first one is the category of all the things which have size at most 1 or 2.
Yes. Exactly, yes. Yes. I have certain rules which must be fulfilled by the partitions, sets of...
What is the description of this one?
This one? So this is a bit tricky. I mean, here blocks of size 1 must there must be an an even number of blocks of size 1. But in addition, you have some rule like this. You can label the points, say plus, minus, and so on. And if you have a pair partition, then it always must connect one plus with one minus sign. For instance, like this. So here I can have blocks of size 1 or 2. In addition, the number of blocks of size 1 must be even. And in addition, the pairs must connect one plus point with a minus point. It's a bit complicated. But why do I do it this way? So suppose that there's an odd number of points in between two legs. Then I have an odd number of singletons in between these two legs. Then I can use this several times, and I will end up with this partition at some point. And then the inclusion is not strict. But here you pick the most complicated of these categories. So here the description is the most complicated one. Okay, so by doing such things, you can distinguish these categories, or what you also can do, you can pass. You can check what are the relations that correspond to such a partition. You compute the C-star algebra, and then you say that you take a representation of this C-star algebra, but not of this one, and then you see that mapping Uij to Uij is not an isomorphism, right?
Are you suggesting that is contained in NC2?
The-
You're saying you have only pair partitions?
Oh, I guess all my arrows are the wrong way. Sorry. Of course, it's all the other way around.
But no, the plus minus thing.
No, that is three.
No, that's correct.
No, that third one consists of all partitions, which they are either of size 1 or 2.
Yes.
In addition, if it is of size 1, you can have only even number of things.
Exactly.
And then if you number the lower points, I'm just confused.
Yeah. Okay. So.
You can assume there are only low points.
Oh, okay.
Yeah. So you also have to label the upper points. Yeah. But you can restrict to those. Yeah.
And how do you prove that the quantum proofs that they obtain are genuinely non-commutative?
What? A gen?
How do you know that the quantum proofs,
Mm-hmm.
I mean the Caesar algebras obtained are genuinely non-commutative lines?
So again,
You have to use representations.
yes. So either I check it on this combinatorial level and say that these are all non-crossing partitions. So this one is not involved, which means that I don't have this commutativity relation. Or you do it with the representations of C-star algebra. Maybe that's...
NC2 is a subgroup, right? And how can they be
And
commutative? What is NC2?
NC2 stands for ON+.
Right, so there is subgroup.
Yes.
So, but is there like, they're all like a subgroup of some, I mean, all have some common subgroup?
Let me see if I got my picture right. Now I know why I'm confused with these signs, because usually I draw this one in the upper right corner and this one in the lower left. I'm sorry. Let me quickly check.
So Sn plus is a subgroup of like all of these pairs, right?
Yes.
And you know that is not commutative for n phi.
Yes.
That will give us proof already.
That's true. Yeah. Okay. Okay, so I think I completely screw up this picture. You should never do this by hand. At least I should not. So all the 7 cases were correct, but let me just get the inclusions right. I'm sorry for that. So this is the way I usually write it, and now my inclusion signs are correct. Okay, so yeah, here I have NC2. Yeah, now it should be correct. Okay.
Because NC2 is the smallest.
Yes.
At the C-star algebra level, you will get quotients of NC2, right? So it's enough to show NC2. The C-star algebra corresponding to NC2 is not.
No, NC.
And C2 is ON plus,
It's the largest one.
and this one is SN plus.
Okay.
So this means these groups, they are all contained in ON plus, but on the C-star algebraic level, it means that they are quotients of the functions over ON plus. That's true. But for having this non-commutativity, I should refer to SN plus.
Okay. Yeah. It's enough to show on goes to X. No, to check that all these things are generally non-commutative. It's enough to check for Sn plus is what.
Yes.
Yeah, but then again, I mean, Sn plus, there's a limit on n, while On plus, for example, is always non-commutative even for 2. So, I mean, actually one should do something more to show, I mean, they're probably not.
Okay, so here what I here what I could do is I mean all these groups, they are of this form.
I mean, if it's commutative, its quotient will be always be commutative.
What is the largest quotient? What is the quotient?
Sn plus is a quotient.
Yeah, that is what I.
Yeah, so this is how I have these categories of partitions. If I pass to the quantum groups, all these signs turn around. If I pass then to the C-star algebras over it again, all the arrows turn around. And then I have something like this. And this is a non-commutative C-star algebra, so this must also be non-commutative.
Yeah, but as I said, you have to take care of the n, while for example, for O2,
Yes.
already you have non-commutative.
At least if n is greater or equal to 4, then they are all non-commutative. For lower dimensions, some strange things may happen. So for lower n, some of these categories might be different but yield the same quantum group, right? Okay. Okay, so these are the 7 non-crossing cases. We can also consider another extreme case, and that is the case of the groups. So theorem, there are exactly 6 easy groups. This means categories containing this crossing, and maybe I can first write it down. Damn, now I'm confused by my own picture. Like this is okay. Right, this should be fine. So I take these categories and I always add this crossing partition. And I see that if I add the crossing partition to this one, these two, they coincide. So these two categories, they coincide. Okay, so on the group level, there are only 6. And the proof is as simple as that. You can just say, if I have a category and another one, and if I take the intersection, then this will of course be a category. Sorry?
I was wondering why they are groups, but it lies between Sn and On.
Yeah, it's in between Sn and On, yes. So this one always yields that the Uijs are commutative. Yeah, so if I take two categories, if I take the intersection, then of course the intersection will be closed under tensor product composition involution and will contain these two partitions. So it's again a category, and we have that if I take any category in this case where I have the crossing, then this is generated by this C0 and X. So this C0 is contained in C. So I have from here to here, that's okay, the inclusion. But in the other direction, if I take a C, then I can, so a partition in here which has some crossings, I can always use this crossing partition in order to permute all the points. Then I get a non-crossing partition, which is in my category. So I have equality here. Okay, so this is not so difficult to check that this is true, which means that the classification of this group case, this follows immediately from the classification of the non-crossing case. So the groups are here. This is On, this is Sn, this is Bn. It's the bistochastic group, which means the group of all matrices where you have this condition. Here you have this group Hn, which is this one. And the other two, they also have a name, but it's Bn prime, and this is Sn prime, and this should be Sn in this Cartesian product with Z2. Something like that. Okay, so you have these 6 groups, and yeah, if you like non-commutative geometry, then you might find it interesting that there are 6 groups, but if you go to the quantum level, there are 7 cases, right? So there's one particular group. If you want to write down a quantum version of it, then you will see that you have 2 possibilities: this one or this one. Okay, so this is like very often in non-commutative geometry. You take a classical object and you want to have a non-commutative analog. But what do you mean by non-commutative analog? Sometimes there are many possibilities of getting a non-commutative analog. Okay, so in here you see that this group on the quantum level splits into 2 different cases. So somehow non-commutativity is richer than commutative world, if you want. At least I want. Okay, so these are our 2 cases, 2 extreme cases somehow, namely on the one side those that are all contained in the non-crossing partitions, on the other hand those that contain this crossing, hence they are groups. But of course, there's something in between, and I mean, my personal point of view for non-commutative things is that at some point you have the classical world, which has maybe it's nice to study. Then you have this world where you really have no commutativity relations. This is somehow the free world. This is also nice to study, but the really difficult part is often in between, right? So this is like with groups. You take Z to some power, okay. This is a commutative group. If you take the free group on several generators, this is somehow the free counterpart of this. But in between, these are the groups that are really, really complicated because you have some relations, but not all commutativity relations and so on. So this is now, we did the lower part and we did the upper part, and let us now come to the difficult part, namely the one in between. So one thing that also, so I should mention that the classification of these 7 non-crossing cases, this was done by Theo Barnica and Roland Speicher in their first paper, and let's say completed by myself in a 2013 paper. And this was also done by Barnica and Speicher in the 2009 paper. Also in their initial paper, they defined half-liberated easy quantum groups. Yeah, so these are quantum groups. These are easy quantum groups, but in fact they are groups. This is what I mean here. So they are quantum groups, but also sometimes a group can be seen as a quantum group, right? So these examples, they are all groups, classical groups, but they can also be seen as quantum groups. And if you see it as quantum groups, then they are easy quantum groups. All half-liberated. So here are all half-liberated easy quantum groups. That is on the level of categories. This means that this partition is in the category, but the crossing partition is not. So now, as I said, now you can start playing around with this, maybe relaxing the commutativity relation just step by step. Here, we say that all Uij commute, but we can say, no, okay, we don't want to have this, so we don't want to have a group, but maybe we have some weaker commutativity relations, so some weaker crossings. And this is a partition which does not imply the existence of this one, but it has some crossings, right? Okay, so you could consider this.
That picture means on three upper points, 3 lower
Yes.
points. Next 3 points on
Exactly. Of course, you can just take a look at the category generated by this partition, and this corresponds to On star, which is the C-star algebra with all Uij, such that these things are self-adjoint and this matrix is orthogonal, of course. And now I have a commutativity relation of this form. Yeah. Is this clear what I mean by this? Or maybe, okay. Okay, so you take 3 different elements, and then you have such a commutativity relation. ABC equals CBA. So A and B do not commute, but a product of 3 commutes in this way. And this is ON star, and this lies in between ON and ON plus. Okay, so on the category level, this sitting between ON and ON plus, this is clear, since this one corresponds to this category, this one corresponds to this one, and of course this category sits in between them, because this one I can always generate with the crossings. Okay, so on the category level, this inclusion is like this. So this means on the quantum group level, it's like this, and this is why.
Why you always demand the non-crossing partitions of log?
Oh no, you've done something wrong.
I did?
Cross should be on ON and B should be the ON.
Oh, I don't know what's wrong today. It's. I always get the inclusions wrong, yeah. So this is the group, this is the quantum group, yes. I'm sorry. But this was not your question, right?
No, that was not.
So what was the question? I always demand that.
This partition, that is
Yeah.
the partitions of non-crossing partitions of size 2 is always there in your
Yeah.
category, right?
Yes.
So,
Why do I want to have this?
yeah, can you remove this and have you? Yeah.
So this corresponds to the fact that I have this relation,
Oh, okay.
and this one is this. So if I want to have subgroups of ON plus, then I need something like this. And of course, in order to get a quantum group, I need that this U is invertible. And this is a nice form of invertibility.
But you use unitary, right? You use self-adjoint in your things.
Exactly. It's self-adjoint and a unitary, hence it is an orthogonal matrix.
Do you get those, the first lecture you defined this A and Q and things like that.
Mm-hmm.
Is there a kind of picture like this for that?
Yes. So now you're forcing me to give some side remarks, but I can give this. So if you have this with this deformed Q, so this comes from modifying this map. So I have a partition, I assign this linear map. I did it in a way saying that here I always check whether equal indices are connected with equal indices, which yields me either 0 or 1 for the delta. If you're not saying 0 or 1, but you also allow some other parameters, then you get this modification. So, yeah. This is for this quantum group, yeah. Okay, yeah. No problem. Okay, so this was one of these half-liberated ones. I wanted to list them all. Another one is, so maybe this is the first one. The second one is this one. And then I also have this category where AHS is this partition. And also this category. Okay, so in this half-liberated case, so yeah, as I said, if you play the game of finding more examples of quantum groups, you can say, okay, I don't want to have that A and B commute, but they commute with this pattern A, B, C. Then you see that this is this partition, this half-liberated partition here. And if you then try to find all the quantum groups, you see that suddenly here there's a whole series appearing. Okay. So there's a series appearing, and this was also one of the nice things that Theo and Roland saw, that there's an infinite sequence. And this is the list of all half-liberated easy quantum groups. And again, you do some case study and you will get this list. So this is somehow, now we defined all the quantum groups that are on this non-crossing stripe and all those that are on this stripe having the crossing, and also we found something in between. But let us now do the real stuff, namely trying to find everything. And it turns out that there's a definition which is quite useful, and this is the one of being hyperoctahedral. So a category is hyperoctahedral if it contains the 4 block, but not the double singleton. Okay, this comes a bit out of the blue, but this is a definition which is useful. Namely, we can have the following theorem. There are exactly 13 non-hyperoctahedral categories. So being non-hyperoctahedral, of course, if it's not hyperoctahedral. Okay, so how comes this? We can prove this by first saying, we can just use the classification results we have so far. First, if my category is non-crossing, how many hyperoctahedral categories were there? Okay, so now I erased this, but there were these 6 categories without the crossing and another one. So which of them is hyperoctahedral? Okay, I can also do the group case first, since this is still on the blackboard. Okay, so in the group case, there are these 6 cases. So which of them is hyperoctahedral? Okay, it must contain the 4 block, so it's only these 3 on the lower side, and it must contain, it must not contain this double singleton. So this is contained in here. It's of course also contained in here, since this is a subset. So only this one is hyperoctahedral. So we have 5 non-hyperoctahedral. Okay. Five cases according to theorem 5.5. As for the non-crossing case, you recall that there were 7 categories, and if you check it, then again only the one which contains which is generated by the 4 block is hyperoctahedral. All the others are non-hyperoctahedral. So here I have 6 cases. And now the third case is C is non-crossing, but it also does not contain the crossing. Non-crossing, yes. Yes, here there are 7.
You have as per the 7 categories in the non-abelian. So if you add the star,
Yes.
then will you get this half-liberated easy?
Yes. Yes. In some sense, this is how you can think of it. But you see that this category here, this did not appear in our non-crossing categories, right?
So that is not the case. With the 7, if you add this one also in the category.
Yes, I will not get this, yeah. So, here for the group case, it was easy. I just took the non-crossing ones and I added this one, and I see what comes out. But for this half-liberated ones, it's a bit more complicated. It does not only mean adding this one. So adding this one, I will get a few examples, namely these 3 examples here. But I won't get all of the examples. It's a bit more complicated there.
And what will be the relation in that 3 article?
What's it for the UIJs, you mean? Yeah, what's it for the UIJs? So this means I only consider 2. I have something like AB to the power S. So I have AB, 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 and so on. And this must be 1, I guess. I hope it's like that. Right now, I'm not so sure if this is really the right relation. Okay, I should check again. But you can write it down explicitly, and it looks little bit like this. Yeah. So. Oh, I think I did not write it down. Okay, I will check what the relation is. Okay, but here classifying these non-hyperoctahedral ones, we have the case of the non-crossing ones. We have the case that it is not non-crossing, but contains this one. Now the third case is that it is not non-crossing and it does not contain this guy. And then we can check that we deduce that the 4 block is not in our category and that the half-liberated is in our category, and thus according to our theorem 5.6, we have 2 cases. Okay, so I don't tell you how to see these 2, but you can, again, just by doing some combinatorics, you will see that these 2 statements are correct, and then we pass to our list and we see that there are only 2 examples fulfilling this. So we have 6 plus 5 plus 2. Okay, so this is the world of hyperoctahedral quantum groups, of non-hyperoctahedral ones, but the really complicated one is the one of hyperoctahedral quantum groups.
Why of the 8?
Well, this quantum group Hn, this is also called the hyperoctahedral group. I can't tell you why for the moment.
The D's product.
Yes, exactly, this rest product, yes. This one is called the hyperoctahedral group. And the category associated to it is this one. And it's exactly, when we had it here, it's exactly the only category which fulfills this definition. This one and not this one. And we will see that now all upcoming examples, they are all contained in Hn+. So they are all subgroups of Hn+. This is why we call them hyperoctahedral. Yeah. A bit indirect, the terminology. Okay, so let me maybe here on let me keep track of what we classified so far. Namely, we had this stripe of all non-crossing categories. So there are exactly seven free ones. And the combinatorics is non-crossing partitions, okay? So we had these 7 objects here. And on the group side, I don't write down all the quantum groups, so there were 6. And the combinatorics was that this crossing is involved, which means that AB equals BA for this Uij. Then we had this half-liberated one, which is ON star. Maybe I'll put it a bit lower. And we also have HN star, which is just given by this category. Okay, here you see that this is in between HN and HN plus. So this is HN star, and these were the half-liberated ones, where the combinatorics is given by having this partition inside, and then this commutativity relation. And we will now see that all remaining all remaining easy quantum groups, they are in this region here. And I will now specify what I mean by this. Namely, I have the following theorem. Namely,
This was Bunny's method.
which one?
Hyperoxide resist motion.
Yes.
Just Bunny.
No, this was also, okay, yeah. So the definition of this HN plus, this was Banneker, Benoit Collins, and Bichon. Banneker, Bichon, Collins. This is from, I guess, 2007. And there they wanted to define a hyperoctahedral version. So they were seeking new examples of quantum groups. They knew there was Sn plus, they knew there was On plus, and they wanted to find an example which is in the same spirit. So they said, okay, let's take a look at this group, at this Hn, which is in between Sn and On, and let's find a free version of it. And then they tried to figure out what is the quantum group, and they said, okay, so this is the group, which is the automorphism group of the cube. And then they said, okay, what would be a free version of this? And in fact, for this group, so again, just a side story, but for this group, this is the automorphism group of the cube. And on the at the same time, it's of this graph. Right? The automorphism group of this one and of the cube is the same. When you pass to the quantum level, you see that these are different objects. The quantum automorphism group of the cube is something else than the quantum automorphism group of this one. And the quantum automorphism group of this one is this Hn plus. Okay. This is how they came to this example. But it was really a long work to get a good definition of this Hn plus. And you see, a few years later, now when this easy quantum group business is developed, it comes really out very natural. Okay, it's just a category generated by this for block. That's it. So this means that this business of easy quantum groups really gives you an immediate machinery of producing examples. This is why Theo and Roland liked it very much when they started with it. Okay, so now we've seen these few examples here, and now the theorem is let C be a category, then either C is hyperoctahedral, and hence one of these 13 cases of theorem 5.8.
13 cases for non-hyperoctahedral.
Exactly. Or it is hyperoctahedral. And or C is hyperoctahedral. And we have that this strange partition is not inside our category. Then C is of the form pk or pl for all L in N, where pk is this partition. So it's hyperoctahedral and a partition of this form. Or in the third case,
Can you explain what is partition?
yeah, I will explain in a second. So first write down the statement, and then I say a word about this. And this one is inside. Okay, now I will say something about this third case later. Okay, but we see that these categories, they split in three cases. Either it's non-hyperoctahedral, then we have it, or it's hyperoctahedral, and then either this partition is inside or it's not. So these are the three cases. So in this case, when this is not inside, then C is the category generated by some pk, which is of this form. I take 4 points, and so it's only 4 blocks, and they look like this. So if I write it as a word, you can write it as A1, A2, and so on up to AK. Then again AK up to A1, A1 up to AK, AK up to A1. Okay? If you take such a word, and if you write down the partition, can you read this? Is this readable? No.
Anyway, I was just struck with the analogy with force Cutler.
Yes. Uh-huh. So.
There's this force Cutler and subfactors,
Mm-hmm.
Jones and Base.
Yes.
And the same kind of.
Oh, really?
Yeah.
So it's this word.
Like you have here this planar picture, you have K colors, right?
Mm-hmm.
And you look at things, you're trying only to things with the same color,
Mm-hmm.
and then they will look like you label them. And you get something very similar.
Okay. Maybe I should take a closer look on this again. Yeah, but the partition here is really you have these. You label it from 1 to k, then you do it in the inverse order, then again the same one, and again the inverse order. Okay, so these are the words. If I draw them as partitions, they look like this, and these are my categories here.
But only 4 long.
It's a partition of 4K elements.
Yes, 4k element.
You split it into first K consists of 4 blocks, dividing into the first K.
No. The blocks. It's k blocks.
Yeah.
Because I connect equal letters with equal letters. So the AKs are connected. All the AKs are connected, so there are 4. And also the A1s are connected. So it looks like this. It's a partition of 4k points having k blocks, each of size 4.
That's strange because those come in a very planar context. These are obviously not planar, they are crossing.
Yes, there are crossings. That's true. Yeah. Okay, I wasn't aware that the same pattern appears there. Maybe we can discuss about this later. Yeah. Yeah. So this is this case, and it has a quite combinatorial structure. As for the third case, oh, I should stop in 5 minutes. Okay. As for the third case, if C is hyperoctahedral and we have this one inside, then we associate a group a normal subgroup FC of the infinite free product of Z2 with itself, or rather FNC with the n-fold free product to C, and the compact matrix quantum group associated to C is given by C star of this free product, the quotient by this FNC, and then the tensor product with Sn. So this means in this third case we have a quite group-like structure. Namely, we have this category of partitions, we associate a group to it, and if we mod out this group, so it's a normal subgroup, if we take the quotient and the tensor product with really the permutation group, this one, the n-fold free product of Z2 with itself. The previous one, this is infinite. Yeah. 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 The infinite free product. Yeah. Yeah. So this is the group in this case. So maybe let me quickly write down this picture here. So this is the here we have always this partition inside, and it means that we have a square b equals ba square, and then here are all my easy quantum groups. So here I have this group stripe, here I have this one, and they always look something like here, this gamma and then this semi-direct product. So this is a semi-direct product. Because my matrix is given by with uaj ij given by ugi vij, where vij is the matrix coming from Sn. The C-star algebra is a tensor product, but this is the fundamental representation here. And this is then called a semi-direct product. And if I denote this by gamma, then I get this semi-direct product. And here is this series with this pk. Okay. So in the very beginning, in my introductory lecture, I wrote down a map of the classification, and this is this map. Okay. So you see, this is the classification of all easy quantum groups with this theorem here. These are the free ones. These are the group ones. These are those hyperoctahedral ones which does not contain this one. As soon as they contain it, they fall in this class. And in some sense, if you want, I feel like that here's a red line. Namely here, these are groups, and these are also, the data comes from groups, whereas this one is really free, and this one there are several hints that this is also a bit more closer to the free world. But we really have to find out precisely what we mean by having such a line here. Okay, I'm sorry that I cannot give you details about this B and C, but this B and C, this was joint work with Sven Raum. So there are 3 papers on this, and the classification is done in these 3 papers. But if you want to see some details, then you can have some private discussion on that, I guess. Okay, so I should stop now because of this lecture at 5 o'clock. Thank you very much.